All right, so let's start. Uh, uh, so we were discussing RTL design, and let's go over the some steps that we have to go through in order to arrive at the RTL picture from the behavioral description that was given. We said that the first step is whatever you're trying to compute, break it up into single assignment statements, meaning that one variable is assigned only once. So x1 is assigned, and then if you have to add up something, then you generate a different variable x2, and so on and so forth. So the first step is to break up your computation into elementary computational steps, which are single variable assignment statements here. The next step was, we said the same thing you can construct, depict it pictorially in the form of a data flow graph, decide which operation you will do in which clock cycle. Then once you have that, then you can look at in which cycle how many variables are needed, and decide what is the number of registers that you would need. If your goal is to have minimum, then this diagram will help you decide what is the minimum number of registers. And once you do that, once you decide your registers, 5, R1 to R5, you decide now how you're going to bind the different variables to the registers, where are you going to store them. And once you're done with that, then you develop your ASM chart. Then you have a description of register transfer statements for each state. And once you have the ASM chart, you can convert it into a data path, looking at the kind of resources that you need, the kind of registers, the kind of functional units, and how you interconnect them. You can determine the data path. And once you have these two pictures here, from there you can decide, you already know the states, how you go from one state to the next state. And from there you get an idea of what are the control signals that I need to send to my data path in order to carry out each one of these operations. And so you have a description of your controller. So you have a complete description of the system at the RTL level. And then, as we said, you can then go from here to the next level, where you can convert each one of them to the gate level representation. How do I implement a register using gates, adders using gates, and all that, right? All right, so let's look at this a little bit in more detail. And so the first step was taking a complex computation and breaking it up into elementary computational steps. Remember, at each step of the design, you have a certain freedom available. And you have to be aware of what is the freedom available at each step of the design, and judicially use that particular freedom, right? So design is always a matter of a series of choices that you make, a series of decisions that you take. And you should be aware of, as much as possible, if I take this particular decision or make this particular choice, what will be the consequence of that? So at this stage, for example, we said you can break it up into elementary computational steps. The thing is that you can break it up in different ways. For example, I could break it up and say, this computation I'm going to carry out like this. X1 is A plus B, X2 is X1 plus C, Y is X2 plus D. I'll do it in this way. Or I could say, X1 is A plus B, X2 is C plus D. And then Y is X1 plus X2. There's a certain freedom available to you at this particular stage, how you break a complex computation into elementary computational steps. And this freedom is going to have consequences. What consequences are? Consequences are always how much area my circuit will occupy, how much time will it take, what is the clock rate at which I can run, what will be the latency, what will be the throughput. And these divisions that you see here, they also have consequences for how much power eventually my system will take. So there are power issues also. Just like delay is there, we are not talking about power. Power will come to us at the circuit level. But there are those issues here. So at each stage, you're taking a decision. Should I break it up like this, or should I break it up like this? Or there are other ways of breaking it up. Okay? And remember, the higher up in your design that you are there, the more crucial the decisions are. The larger the impact of those decisions will be. If you decide to do some things in parallel, you can see you're doing it sequentially here, and you are doing some things in parallel. Now, that will have a huge effect on the eventual quality of the design than steps that are lower. Each step has obviously an impact. But the higher up you are, the choices that you make, in general, the larger the impact would be. Okay, so these are very, very crucial stages of design. Anyway, in this case, so all that I'm trying to tell you is that at each step there are choices and there are decisions to be taken. And so one should be aware of, for example, how do I break it up? Okay, fine. So if we take the next one, we already saw if you break it up in this manner, then this is what you do. So if you break it up in this particular manner, A plus B, C plus D, X1 plus X2, then the next step, as we said, is the data flow graph. So we represent it in this manner, A, B, V1, V2, this thing here, all right? So we represent it in this manner here. And now note that once I represent it like this, the next step was, I have all these operations. I have 3 operations here, V1, V2, and V3. 3 operations that I'm doing. All of them are addition operations. Now, when I trying to schedule it, scheduling means which clock cycle will I do which operation, right? That's what scheduling here means. At this stage, also note that I have freedom. I could schedule V1, V2, V3 like this here. I could also, there's nothing which is telling me I can still schedule V1, V2, V3 like this here. So there's a freedom in terms of how you schedule the operations. Now, if I schedule it like this, I'm carrying out 2 addition operations in 1 clock cycle. Obviously, I'll need 2 adders. If I schedule it sequentially like this here, then I'll need 1 adder. So your scheduling has implications, and there are usually freedom in terms of how how much. So there's a freedom available in terms of scheduling, and I have to use that freedom. I have to make a choice. So sometimes you may, whatever comes into your mind, you may just do it. But as I said, that's not the better way of doing design. At each stage of the design, what you should do is you should generate alternatives, explore the alternatives, see the implications of each one, and then make an informed choice. This is not something that comes to my mind, let's fill it up and go forward. That's not the way to do it, okay? So you should be aware of what is the freedom available at this stage of the design. So for example, in scheduling, so let's take a different example. All our examples are addition, subtraction, multiplication, simple examples like this, okay? So let's say we have an example like this here, A plus B plus C plus D, A dot B minus C. So this is what we want to do. And we break it up in this manner here. So as I said, there may be other ways of breaking it up, but that's not the focus right now. So this is the data flow graph that I generate, okay? A plus B, X1 plus C, D. So this is the one set of computation that is occurring to produce Y. And Z is the other set of computation that is occurring to produce the output Z here. Okay. So let's say we have broken it up in this manner, and this is the data flow graph. So our issue was scheduling. Now, in order to find out what is the freedom available in terms of scheduling, what we can do is we can do a scheduling which is called as soon as possible, ASAP. Which means that as soon as the inputs are available to a particular operation, I schedule it. If the inputs are available, in clock cycle number 1, schedule it in clock cycle number 1. Okay, so that's the idea. As late as possible, it's just the opposite. I'll schedule it as late as possible, the operation here. So let's look at that. ASAP would be inputs are available. So in the first clock cycle itself, I schedule V1. Now V2, I cannot schedule in the first clock cycle because it has to wait for input for this one. But V2, the output of this one, X1, is available in clock cycle 2. So V2, I immediately schedule it. And then for V3, I have to wait. So the earliest I can schedule is over here, V3. Now V4, the earliest I can schedule is here. And V5, the earliest I can schedule is here. So simple, as soon as possible scheduling. As late as possible scheduling? Well, we are going to use a 3 clock cycle, let's say. Late means, well, you can make things as late as possible. You can unnecessarily introduce a lot of clock cycles. We don't mean that. Okay, so we look at this operation and we decide 3 clock cycles are okay. So now, what is the latest that I can schedule? So here, note that I schedule V1, and then I schedule V2 and schedule V3. There's not much choice that is available. But note that since the output is going to appear here, right, output of Y is appear here, V5 that you see here, I can schedule here. It's not going to make any difference. correct? The output is available here, the second output is also available here. So I can schedule it as late as this. And still, I'm doing my computation in 3 clock cycles. And V4, then, because V5 is carried out here, so V4 I have to carry out here. Okay, so this is also possible, as late as possible. Okay, without unnecessarily introducing more clock cycles, more states. That we don't want to do. Okay, so this, keeping in mind, then this is as late as possible. So now, if I examine, these two are, in some sense, two extremes. As soon as possible, as late as possible. So what we can do is, we can say, well, what is the freedom available in scheduling? If I look at V1, one extreme and the other extreme, let's say, then V1 has to be scheduled in first clock cycle. V2 has to be scheduled in second clock cycle. V3 has to be scheduled here. V4, if I look at it, I can schedule it here or I can schedule it here. So we can say this is the freedom available. And V5, similarly, can be scheduled here or can be scheduled here. So this is the freedom available here. So if I construct a chart like this, it tells me what is the freedom available in scheduling. And now I decide. There's no choice here, V1, V2, V3. I have a choice here, V4, and I have a choice here. Okay? So I decide on this basis, should I schedule it here or should I schedule it here? And of course, it will have implications for the other choices also. So what we are saying is, when we are talking about scheduling, how to schedule which operation in which clock cycle, what you can do is you can construct a as soon as possible scheduling chart and as late as possible scheduling chart. And from there, then all that we are trying to do by looking at these two extremes is to look at what freedom do I have? How much freedom do I have? Okay, so becoming aware of the freedom that is there. So becoming aware that there's a freedom in scheduling V4 and there's a freedom in scheduling V5. Okay, and now accordingly, now if we look at it, there are 3 possibilities that you can see here. I can generate these 3. V1, V2, V3, so there's no, this thing here, V4 I could schedule here and V5 here. V4 I could schedule here and V5 here. V4 I could even schedule it here and V5 here. That's also possible. Now, is it making any difference? Well, if we look at it, all require one adder, one multiplier, one adder, one subtractor. So if we look at the resources required, I require an adder and a multiplier here in the same clock cycle. So I need at least one adder, one multiplier. If I look at this, I require an adder and a subtractor. So I require one more subtractor. So we can see all 3 require one adder, one subtractor, one multiplier. So in terms of resources, they all are the same. Will they differ in terms of how much time latency or clock period or throughput or anything else? Do they differ? What will decide the clock period in these cases? What will decide the clock period? Remember what you are doing? You are going from one register to the next register, right? You're taking the output of some register, going through some adder multiplier block, and then storing the result again in a register. So it's a register to register delay. That's what we saw. And for the timing, if you forget about the register delays, clock to queue delay and setup time and all that, and think about adder and subtractors and all that have the maximum delay, then we note that multiplier in general is a much more complex entity compared to an adder or a subtractor. Its delay is going to be larger. So my clock cycle here will be determined by the multiplier. I have to carry out a multiplication operation. In each one of them, even here I have a multiplier, even here I have a multiplier. So will the clock cycle be determined by, will the clock cycle be the same? Well, if I look at it, note the result of the multiplication is required in the next stage, right? So how much should be the clock cycle? Clock cycle time period should be at least equal to the time taken for multiplication to occur. Okay, so and each clock cycle is the same. We don't use a different period here and a different period here. That's too complicated. So, right, in all these systems is the same clock, same time period everywhere is the same here. So my time period is going to be decided by the multiplication time. Here I have to carry out addition, 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 but here I have to carry out multiplication. Again, the time period is going to get decided by the worst case scenario. So it's by here. This also is the same. This is an interesting case though. This is an interesting case where note that I have to carry out the multiplication process, but it's not required here in the next clock cycle. the result. The result is required here. So potentially what I could do is, I could spread this multiplication over 2 clock cycles. I could do that. Alright, so this is what we call as multi-cycling. Multi-cycling means my operation is done not in 1 clock cycle, but I give it 2 clock cycles. Multi-cycles. Right here, in this view is, all operations are done in single clock cycle. The whole multiplication has to be done in single clock cycle. Addition has to be done in a single clock cycle. If we allow that freedom of multi-cycling, then this gives us an interesting possibility, that I can spread the multiplication over 2 clock cycles. And if I do that, spread the multiplication over 2 clock cycles, now you know that and let's say then basically the clock period will be half the multiplication time. Okay, so there are 2 other possibilities. One is called multi-cycling, and the other one is called chaining, that you can do here. Now, what do we mean by chaining? Chaining is that I do 2 operations in the same clock cycle. I chain 2 operations and do it in the same clock cycle. So for example, when we were looking at V1 and V2, what I do is I chain both of those operations and do it in the same clock cycle, V1 and V2. And then I arrive at V3, and then this is how it is. So I've changed 2 operations. Can you see an advantage? Earlier, remember, earlier picture was that each one required 1 adder, 1 subtractor, and 1 multiplier. And my clock period was determined by the multiplication time. Now let's look at this one. Does it require more resources? How many adders and subtractors and multipliers? So I require 2 adder and a multiplier. I require an adder and subtractor. So what I can do is, I can have basically blocks which are adder subtractor blocks, right, with the select input. So if I give some select input, it adds. If I give some other select input, it subtracts. So basically, here also I require 2 adder subtractor blocks and 1 multiplier. Here also I require 2 adder subtractor blocks and 1 multiplier. So if we compare these 2, then these 2 are similar in terms of resources. But note, I require 2 clock cycles here. I require 2 clock cycles, and this would be especially interesting. Let's say if the multiplication time was 6 nanoseconds and addition time was only 2 nanoseconds. So even if I chain it, 2 nanosecond and 2 nanosecond, it becomes 4. Multiplication is still 6. So my clock period is still determined by multiplication. But I end up doing it in 2 clock cycles. So latency becomes 2 clock cycles instead of 3 clock cycles that we were seeing. So chaining, you can see that, so that's the other freedom that is available to you. Okay, I can chain operations within a clock cycle. The other one that we said was multi-cycling. That instead of carrying out 2 operations in 1 clock cycle, what I do is, I take an operation and I carry it out over more than 1 clock cycle. So I spread this thing over 2 clock cycles. So in this case also, you know that I require 2 adders and 1 multiplier. So resource-wise is the same. But again, note that now that I have spread the multiplication over 2 clock cycles, each clock cycle can be much shorter, can be half the multiplication time. And therefore, I can arrive at a faster system. So this is the other thing that, so in scheduling, what we are saying is, you can construct as soon as possible schedule, as late as possible schedule, draw a graph like this here, a graph like this, end up drawing the different possibilities that are there of scheduling. You know, look at the implications of each one of them in terms of resources, in terms of time. And then you can also keep in mind, well, maybe I can do this. I can do multi-cycling or I can do chaining. And if I do that, does it result in any benefit to me or not? So these are some of the freedoms that are available to you when you are doing scheduling. What we are doing is we are taking advantage of the fact that multiplication is a more complex operation requiring more delay. So it says that, you know, when you are scheduling, you have to be aware of what multiplication algorithm am I using, how much time does multiplication take, how much time does an addition take. So all these data should be available to us to make these kinds of decisions. If I'm doing an operation, I have no idea of its delay and all that, then obviously, you know, I can't decide whether to chain or not to chain and all that, or whether to spread, to do multi-cycling or not. Okay. The other one is the concept of, remember we used the concept of pipelining. Pipelining was that when you give a data to an input, don't wait for the system to process that particular input completely and then produce an output and then give the next input. The idea is to break the processing into several parts. One part may be processing data which is xn, another part may be processing the data which is xn minus 1 in the previous clock cycle, and the third part may be even in the clock cycle before that. So the idea is to break it up, and the advantage was, yes, latency may remain the same, but the throughput will increase here. So in this case, what we are talking about pipelining, but pipelining the loop. Okay, so let's look at this addition operation again. A dot B, C dot D, E dot F. We break it up into individual assignment statements. We construct a data flow graph. Okay. We take the data flow graph, do a as soon as possible scheduling. We decide 3 clock cycles we are going to use, 3 states. We do as late as possible scheduling. You can go over these steps yourself later on. So, if I look at, so let's say I decide on using, I'm not going through that freedom and all that. Let's say I decide to use as late as possible scheduling. Yeah. Okay. For this particular part here. Now, if I start looking at resources in state S0, V1 and V2, if you look at, I require 2 multipliers, no adder. So look at this one here. In state S1, I require 1 multiplier. V3 is a multiplier and V4 is an adder. So I require 1 multiplier, 1 adder. In state S2, I require 1 adder. So that's how I'm using my resources. So obviously, if I look at it, I require 2 multipliers in my system and I require 1 adder in my system. So 2 multipliers and 1 adder, if I go ahead with this scheduling, are required in my system. Now, once I have used 2 multipliers and an adder, what I'm looking at is, well, fine, I've scheduled it. How good is my resource utilization? So, okay, so I'm using multipliers quite effectively here. I'm using only 1 multiplier, it's lying idle, and the other multiplier is not being used at all. And similarly, I have 1 adder, which is fine. So what I can say is, on an average, the multiplier utilization is 50%. So I could have potentially used 2 here and 2 here, potentially. So 6, and I'm using only 3 times in this one. So 50% utilization. And I could have used adder everywhere, let's say. The utilization is 66.6%. Yeah. Anyway, so can one improve the utilization of my resources once I put in there? And also, what we're looking for is here, the latency is 3 clock cycles. The throughput is also every 3 clock cycles I can read the data. So the idea is that can I improve things? So now one of the reasons for underutilization of resources, if you look at this, is I have 2 multipliers available. I read the data and carry out multiplication. Then I go to the next stage. And I'm doing 1 multiplication, 1 addition. Then I go to the next stage. And while doing that, I'm basically waiting for the next series of computational steps to get over to read the next set of data, right? So one of the reasons, if you examine the schedule for underutilization of resources, is that the next input is processed only when the processing of the first input is complete. If there are several stages of computation, then except for one stage, all other stages remain idle, resulting in underutilization. Well, I can't carry out these 2 multiplications unless this is over and this is over, and then I come back to the first stage, right? So the idea is process multiple data simultaneously. Your system doesn't process one data which has been read, but it processes several data simultaneously. But different data undergo different computations using different set of resources at any given time. So look at this particular picture. It is the same that one I'm drawing, V1, V2, V4, V3, V5. All that I'm doing is, instead of V1, V2, I'm writing, just to make it easier, that these are multiplication. So I've made it M1, M2. V4 is what was V4? V4 was addition. So I made it add 1, A1, and then this is M3. So it's the same schedule, right? M1, M2, A4, M3, A5, right? So 2 multiplications, an addition and a multiplication and an addition here. So in loop pipelining, what we are saying is that Note the second schedule, what we have done in the second schedule. M1 and M2 we do, A4 and M3 we do. And then this part, instead of assigning it a new state, S3, what we are saying is this part is going to be done back in this particular state, in the first state itself. In the first state itself. Note that the output of these M3 and A4 are taken and put back into the first state itself. That's where we are going to do it. So now note that when I'm doing M1 and M2, what am I doing? On current data. M1 and M2 are processing the current data that has been read. What is this processing? The previous data is processing. And there's no conflict. This is processing the previous data. This is processing the present data here. So I can do that. So I have this kind of a freedom here. I have pipelined my system. Earlier, the same data was being processed here, 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 here. The data xn that came in the nth clock cycle is processed here and here and here. While here, this is n, xn, all that, but this is xn minus 1, the data which came in the previous clock cycle. So I can do that. I can process this one here. Now note that if I do that, well, one benefit, of course, you see throughput is improved. Utilization multiplier is 100%. Adder is 100%. Adders I'm using everywhere. And multipliers are, utilization is also 66%. Better usage of my multiplier that is there here. Right? So although each input data still goes through a delay of 3 clock cycles, which we've been calling latency, after I read the data, here after 3 clock cycles the output is produced. Here also after 3 clock cycles, 1, 2, and back here 3. Here also 3 clock cycles, so latency is the same. But the rate at which input can be processed, which we call as throughput, has increased from 1 over 3t to 1 over 2t. That's the rate at which I can read the data and process it. Okay, so I've improved that by using the concept of loop pipeline. In the loop itself, taking one operation and putting it back into another one and doing it together. You need not finish with one data and then read the next data, which is obvious common sense. You don't finish with, you don't just wait. That's the concept of a pipeline. You don't just wait. And, whenever somebody comes in, let's say you go for an admission process, you see a lot of desks that are there. It's not that one student comes in and then goes at one desk, his check, then goes to the next. After that, he's all done. Then you let the next person come in. We pipeline it, right? One student goes to the next desk. Well, a new student comes in. So different students are being processed at different desks, right? So we pipeline that. It's something that we do. I mean, it's common sense, right? So you break it up and you do. It doesn't make sense to finish with one student and then ask the next person to come in. It doesn't make sense. So same thing that we are doing here. So earlier we were saying, well, this is what you do. You finish with one set of data, then you take in the next set of data. Right? Now we are saying, well, go ahead and read the next set of data also and process it. Okay? But then, so this is the other freedom that is available to you. That this is what is called as loop pipelining. Can I take my loop that is there and pipeline it? In the sense that now different operations are being done on different sets of data. Now, in general, what you will find is that if I do loop pipelining, more registers may be required. Okay, so let's look at this one. These operations that you see here, I have still V1, V2, V3 and all that, but still M1, M2, A4, M3, A5, and these are 2 operations here. Let's look at we said how many registers are required. So what we do is we take this particular schedule and we look at clock cycle by clock cycle, where are the variables required. So if I look at A is required for M1 or V1, same. So A is required here, B is required here, A, B, and C and D. C and D come to M2, so C and D are also required. E, we are doing in, note that E, we are scheduled it in this one here, so E is required, E and F are required till here. I read it, it's required here, and it's required here, the variable E. Okay, E and F are here. And similarly, we look at X1. X1 is becoming available as the output here. So X1 is here, X2 is here. And like that, you fill it up, X3 and X4 here. Where is Z available? Note that after coming from this, where do we go back? We go back to the first stage here. So the output of this, where is it available? In this clock cycle. So that's why Z is put over here. Okay, note that Z variable, where is it stored? Once you go through that, once the next clock edge comes, right? Once the next clock edge comes, where do you go? From S3, you go back to S0. So that's why Z is required. So we fill it up and we look at where are the different variables required in which clock cycle, and we look at the density here: 1, 2, 3, 4, 5, 6, 7. So we need at least a minimum of 7 registers. Each clock cycle we examine. Well, in this case we require 7 registers. In this clock cycle, well, maybe 4. In this 2, but maximum is 7 here. So I need to use at least a minimum of 7 registers. If we look at this one, so again we go back and look at M1, M2 and all that. We fill up this chart here. We find here how many do we require? 1, 2, 3, 4, 5, 6, 7, 8. 8 registers are required. So here 8 registers you'll have to provide in order to store the relevant variables here. So in general, when you pipeline a system, when you do that, it's understandable when you pipeline, because pipeline is what? You're not only processing the present data, but the previous data also. So it's obvious that I need some storage for previous data also. If you're doing simultaneously present data and past data also, some storage is required. Yes, so you'll end up using more registers, but it may be worth the price paying. When I'm going from 7 to 8 registers, what is the percentage increase in area? Not that much. 7 to 8. Plus you have multipliers, adders and all that. So the area increment or in terms of that is marginal, but I end up doubling my throughput. Okay, so it's worth the price. Very little price you have to pay, and it's worth the price that is there here. All right, so that's the other thing to be aware of, the concept of loop pipelining. In terms of how do I schedule my operations here? Can I pipeline my system and do operations simultaneously? Okay. So we have seen as soon as possible scheduling, as late as possible scheduling, to give us an idea of the freedom that is available. Looking at chaining of operations within the same clock cycle, multi-cycling, taking an operation and allocating more than one clock cycle to carry it out, and loop pipelining. Pipelining a loop in order to carry out the process here. Okay, another freedom. So we said once you schedule, so let's say this is a schedule which is there here. Okay, so it's some computation you're doing and you've constructed the data flow graph and you've scheduled the operations and all that. Now, how many adders do we require? How many adders do we require here? Two adders that are required? You all agree? Okay. So adder 1 and adder 2. Fine, we know 2. Now how do I, so this is an operation V1 and this is an operation V2 and this is an operation V3 and this is an operation V4. Now we have 4 addition operations and we have 2 adders. Now we have to allocate the operations to the adders, which is what is called as operation binding. So note that I can do the following. I can take adder number 1 and I say adder number 1, adder number 1 is going to carry V1 and V3. And adder number 2 is going to carry out V2 and V4. Okay. I can also say adder number 1 is going to carry out V1 and V4. And adder number 2 is going to carry out V2 and V3. Obvious, right? You say, why are you doing it? These, as I said, these are toy examples. Why are you doing it? Because you can see it. You can see, well, it doesn't make sense, right? This one obviously makes sense, this doesn't. But if you have a more complicated schedule, it's not obvious. So the issue is not that in this case it's obvious and another. The issue is in general you will not, just by looking at it, you cannot tell what is the best way of binding an operation. So again, I'm raising issues. I'm saying, fine, you have decided that I have adder 1 and adder 2. There's a freedom available to you. I can do V1 and V3, bind it to adder 1, and I can do V1 and V4 binding it to adder 1. Or I can do V2 and 4, and this freedom is available. And in more complicated cases, it's not going to be obvious because you'll have data here which is going into this particular one and this particular one. It will be more complicated, right? And so it's not available to you. Now, the point is each one of them will have consequences. Okay? What consequences do you think these two will have? Case 1 and case 2. Still the same number of adders, same number of registers. What consequences will it be there? Between these two. If I do this versus this. What will be the difference between these two? Same ASM chart will be there. Right? Same operation I'm doing in same clock cycle and all that. So everything else is the same. So the other one is, so this is one. I'll go forward and talk about. So this is operation binding. The next one is variable binding. Well, we can decide from this particular picture that, you know, if we look at it, we say A is required where here, because A is required in first and the second one, A is required here, B, C, D, you know, all that we can say. So we say, well, 1, 2, 3, 4, 5, 6, 6 registers are required. Now I have to bind the variables to the registers. I can take case 1, A, B, E, C, F, D, G, H. That's how I can bind. I can assign the variables to the registers. I can do this also. I can assign it in this way also. You can think of other ways also. So the point is, yes, you've decided how many registers to use, how many adders to use, but now the operations have to be assigned to adders, the variables have to be assigned to the registers, and there's a freedom available to you. So I have two cases, right? I have case 1 and case 2, and I have case 1 and case 2. So let me take the worst of both of them. Okay, so case 2. Case 2 is where I'm, you know, you can obviously see I should not bind V1 and V4 to the same adder. I should not do that, and I should not bind V2 and V3 to the same adder. All right, but let's say I've done this. I've taken a case 2 here and a case 2 here. Now, to see the implications, let's construct the data path. So how do I construct the data path? What is my first step? What do I do? Let me draw the two adders. Adder 1, adder 2. I'm adding V1 and V4 here and V2 and V3 here. Right? The outputs of this are going to be E and H. So I've written here E and H and F and G here. The two adders are here. What are the, let me draw next the registers. R1, R2, R3, R4. And I know what I'm binding in these A, B, C, D here. So we put that. R5 and R6. Now note that A, B, C, D are fine. R5 is being shared between two variables and R6 is being shared between two variables. What do I need to put? Multiplexer. So I put mux here. Mux is here, shared. Where are G and H coming from? So I look at from here. Where are E and H coming from? I look at here. Okay. Now, where does adder 1 receive inputs? Adder 1 is adding A and B. And also adder 1 is adding V4. V4 is what? F and G. So how do I share it? We put a mux. Sometimes it will receive from R1, sometimes it receive from this R2, sometimes it may receive from here. So I share. Okay? Fine, we have constructed the data path. We looked at the adders, we drew all the registers, and the variables have to go into these registers, so we use muxes. Adder is being shared, so we use muxes. And how many mux do I require? 6 mux. So now addition was, so we had already decided on how many adders. We had already decided on how many registers. Muxes are the interconnect units. Whenever I'm sharing, I have to use muxes here. Okay, so that's one way of. The other way of sharing is you don't use mux, you use a concept of a bus, which we'll come to later on. You know, you put the data onto a bus, and the same bus is nothing but a set of wires, a set of common wires running through your system. And so you put the data on the bus. You know, so if R1, let's say you want to transfer data from R1 to R2, so R1 puts the data on the bus, and then R2 takes the data from the bus and reads into it. So one common interconnect unit here. Anyway, so this is 6 muxes. Well, what is the clock rate of this system? I have to evaluate. So I know now, well, the interconnections you are seeing, even when you are using muxes, you realize that eventually I'll have to implement it physically. And I will have all these four wires running back and forth. Wires running here, wires running here. This is going to create a problem. You know, when you are actually going to make these things on a chip. Running wires back and forth is going to create a problem for you. Alright, 6 muxes are there. Now what is the clock rate at which it will run? I have to examine the worst case path. So I look at the worst case path. So remember, what you do is you look at the delay from one register to the next register. That's what happens. In register transfer level, the data is going from the output of a register back to the input of a register after going through some computation. So I look at my system and I say, well, let's suppose the data starts from here, R1. Goes through a mux, comes here, goes through an adder, goes here. So remember, so when you read A, there's going to be a clock to Q delay. Only after when a clock edge comes, there's going to be a delay which is clock to Q delay of R1. Clock to Q delay here. Then there is a mux delay here. Then there is an adder delay. After an adder delay is available here, it goes here, let's say, here. Then there is a mux delay here. After a mux delay is available here at this point. And it must be available a minimum of setup time before the next clock edge. And so that's what the setup time of this particular register. So if I examine the critical path in my system, I arrive at this. So my clock period must be equal to greater than this. So note that I have I have an adder delay and I have clock to Q. So these are always going to be there, clock to Q and setup time, adder delays, and there are 2 mux delays, which are also added here. In the next case, case 2, which I'm not showing, case 2 was what? Case 2 was taking the, So the next one is case 1 actually. Okay, case 1. Case 1 where I took the case 1 of the best cases for both of them. And then I implement it in the same way. Now note here, you can see much cleaner implementation, right? You don't have all these wires running back and forth. Look at this one. Look at the complexity, running wire here, all this. And look at this one here. Very neat breakup of the system. And so I require only 2 muxes here. So note that the complexity is, or the simplicity is even more than simply measuring in terms of mux. Yes, I have 2 muxes compared to 6 muxes earlier. But also note that no wires running back and forth. And when I look at the overall delay, I require only 1 mux delay here. But one sort of overlooking part is, when you look at, let's say, the delay, we're not counting the delay of the wires. If I have long wires running into my system, all these wires carry capacitance and they cause a delay. So I'm not even counting that. So this one, besides having 1 extra mux delay, will have probably a lot of wire delays. While this one, maybe with shorter wires, may be a much cleaner system. Okay, so all that is this example is trying to illustrate is that you've decided how many resources, how many adders. You've decided how many registers. But how you bind the variables to the registers and how you bind the operations to the adders and subtractors is going to have an implication on how simple or complex your circuit is. Okay, in one case it may be a lot more complicated, in one case it's going to be a lot more simpler. So my whole point in talking about all of this using these simple trivial examples are to make you aware of the issues that are there at each stage of the design process. This is the freedom that I have. There are many ways of doing it and one needs to explore. At every design step you have to explore. You have to explore the alternatives. Okay, and one last example that I had was, and we'll be done with our RTL. So this is, instead of doing only addition, so I said, let me do some little bit of more realistic example, which is a multiplication. So very quickly, what I'm going to do is in the next 1 minute. So suppose I want to design a chip to carry out multiplication. So I have two variables here. I multiply them together to produce an output Z. There's a start pin here. So when I press start, then the multiplication starts. And once the multiplication is over, there is an output here which says done. Multiplication is over. The result is available here. So the first thing is, remember at the top level, when you look at it, what algorithms do I use for multiplication? So in our case, we'll use very simple algorithm because we have to keep things simple. So multiplication by repeated addition. Right? So this is what I do. This is my algorithm. If start is equal to 1, then I read AB, done equal to 0, some temp is some internal register. While A is greater than 0, I loop A minus 1, temp equal to temp plus B. I keep on adding B till I have something in A. multiplication by repeated addition. And while whatever is stored in temp, I output it to Z, done equal to 1. Okay. Very simple algorithm for doing multiplication by repeated addition. Next thing, what do? I construct a data flow graph, except that this data flow graph has to be slightly modified by adding a control part here. So if start is equal to 1, read AB, done equal to 0, temp equal to 0, A greater than 0, do this, A, this thing, do this here, back again. Next, I schedule it, 2 states, S0 and S1. We assumed a mealy machine. We identify the registers. Once we identify the registers, we construct an ASM chart. And once you have an ASM chart, then go ahead and construct the data path, and you can construct the controller. So controller data path is here. Okay, so we have a controller data path. And from there, we get the control inputs. We require 2 states here. We generate the control inputs. And that brings us to an end of how you go through your RTL design. So from the description, decide an algorithm, break it up, schedule it, and arrive at a data path controller and generate all that. Okay. So please, I've skimmed through this, go through this particular example in detail. Maybe you can think of better multiplication algorithms. This is very simple, and think of how you will carry it out. Okay. So let's stop here.